So the last unit in this topic is looking at electrons and how they behave in atoms. Now, by the end of the unit, you should know particular learning objectives and also should be able to do certain learning objectives. It's up to you to go through these learning objectives and make sure that you understand them and have completed them. So, in terms of electrons, let us look at something called ionization energy. And we're going to relate it back to the earlier topic around electron configuration and the structure of the atom. So the ionization of an atom involves the loss of an electron to form a positive ion. And the first ionization energy is defined as the energy to require 1 mole of electrons from 1 mole of atoms when that atom is in the form of a gas. And here is the equation. So you've got a gaseous atom X, so you basically heated it to a large with a amount of energy until it's a gaseous form, until it begins to ionize. It loses an electron to become a positive ion. And this first ionization energy is represented by this equation. Now notice that delta H is positive, because since all ionizations require this energy to actually allow the ionization to occur, they are an endothermic process. Remember from last year, endothermic processes are ones in which require energy for them to occur. And therefore you have this positive enthalpy change, this delta H value. So in terms of relating it back to the emission spectrum that we investigated in the first unit of this topic, as the electron moves to high energy states, remember we said that the spectral lines converge. Okay, so basically we're looking at this part here. Okay, the lines converge because the energy required to move from these later energy levels is getting smaller and smaller and smaller. Okay, the distances between the energy levels are getting less and less. So the upper limit of this convergence, okay, I guess when n equals infinity, is the amount of energy it takes to remove this 1 electron from the atom to form the ion, and this is known as the ionization energy. So from your data booklet you have these two equations which we briefly touched on in the first unit. C equals nu lambda and E equals Planck's constant times nu. Okay, where C is the speed of light, H is something which is called Planck's constant, which you're given. Mu is the frequency, which is given in hertz, and lambda is the wavelength. And finally, energy is capital E in joules. So, using those two equations, let's look at some problems. So, determine the energy of a photon of red light given the wavelength is 650 nanometers. Okay, so pause the video now and let's see if, using those equations in the previous slide, you can answer the question. Okay, so the first thing you have to do is choose which particular equation you're going to use. Okay, so you've got to find the energy. You're given a wavelength. Okay, so I would go for C equals nu lambda because we know what C is, we know what the wavelength is, so we just have to find the frequency. Okay, so it's going to be 3 times 10 to the 8 meters per second equals nu times 650 times 10 to the negative 9 meters. Remembering, of course, that you're converting into meters from nanometers. So it's going to give you a nu of 4.62 times 10 to the 14 seconds to the minus 1. Okay, so then we can, since we've now found nu, we can use the second equation where energy equals Planck's constant times nu, this frequency. Okay, I'll just rub out these things. Okay, so now we have the number, okay, the frequency, nu 6.63 times 10 to the negative 34 joules seconds times 4.62 times 10 to the 14, okay, because this is Planck's constant which you're given. So then, plugging in the numbers, you get the energy, which is 3.06 times 10 to the negative 19 joules. Hopefully got that correct. So looking at a second problem, determine the first ionization energy of hydrogen, the atom hydrogen, given that the shortest wavelength line in the Lyman series is 91.16 nanometers. Okay, so again, pausing the video and trying to work out, I guess, initially what the correct equation to start off with is. Okay, so welcome back. So the shortest wavelength will be the line of convergence. That's the first thing you have to recognize from the question. And hence, this will represent the ionization energy. And its units are kilojoules per mole. Okay, it's the amount a mole of electrons is lost from a mole of atoms. Okay, so again, using the correct equation. So we're going to start off with C equals nu lambda. Okay, because we have the wavelength, you can then find out nu, which is given 3.29 times 10 to the 15 seconds to the minus 1. Okay, again, you're looking into the second equation now that you have nu. So using the numbers, you end up with the energy being 2.18 times 10 to the negative 18 joules. And the ionization energy, therefore, is going to be number of photons per mole times the energy per photon. So we know that the number of moles is going to be exactly 1 mole, 6 times 10 to the 23, so we want to get into kilojoules per mole, times this number we just found out for a mole of electrons. So it's going to be 1312 kilojoules per mole, because remembering that the units are in kilojoules per mole. So you've got to be careful with the unit conversions. So what are the factors involved in ionization energy? So the value of the first ionization energy depends on two particular factors. Okay, how big the nuclear charge is, so the number of protons, okay, what atom it is basically, and the energy of the electron that has been removed. And this also depends on the distance that electron is from the nucleus. Okay, so as the size of the nuclear charge increases, the force of attraction between the negatively charged electrons and the positively charged nucleus increases. Okay, so you can see that here you've got 1 proton here. Okay, you've got 3 electrons floating around. The smaller the nuclear charge, there is a smaller force of attraction, and therefore you have a smaller ionization energy. Okay, as you increase the number of protons in the nucleus, the positive charge of the nucleus increases. So with a larger nuclear charge, you get a larger force of attraction. So therefore you have a greater ionization energy. It requires more energy to remove those electrons because there's more pull from the positive nucleus. So the second factor in terms of ionization energy is going to be the distance of the electron from the positive nucleus. So as the distance of the electron from the nucleus increases, the force of attraction between the electron and the positive nucleus will decrease. Okay, so the further away the electron is, then it's not feeling the force of attraction from the positive nucleus as much as if it was closer. Okay, so electrons closer to the positive nucleus will have a larger force of attraction, therefore will have a greater ionization energy, and those that are further away will have a smaller force of attraction and therefore a smaller ionization energy. Going across a period, the size of the first ionization energy shows a general increase. Okay, and the reason why is because the electrons are on the same energy level or same shell, but the size of the nuclear charge begins to increase because the number of protons increases as you move across the period. Okay, so going across the period, the positive charge on the nucleus increases, even though the number of electrons does increase. There's more effective charge from the positive nucleus, more pull. So continuing along with the ionization energy trends across the period, the first ionization of aluminium to aluminium 1+ is less than that of magnesium. Despite the increase in number of protons, obviously, in the nucleus, and the increased nuclear charge. So just looking at the results here, these are the numbers. Okay, so for magnesium, it's 736 kilojoules per mole, and then for aluminium, okay, so we're looking here, it's going to be 577 kilojoules per mole. So pause the video now and just think of an idea why you think that aluminium's ionization energy is going to be less than that of magnesium's. Okay, so what you really should have noticed is the difference between these two is this p electron. Okay, so the reason why you see this difference in numbers is because the outer electron for aluminium is removed from the p orbital, which is a high energy sublevel. Whereas for magnesium, it's only from the 3s, which is of lower energy. So it requires more energy to remove it from the p sublevel. Okay, so again, looking at the trends, the first ionization energy of sulfur is less than that of phosphorus. Okay, despite the increase in the nuclear charge. In both cases, the electron removed is from the 3p sublevel. However, the 3p electron removed from sulfur is paired, okay? Whereas the 3p from phosphorus is an unpaired electron. Okay, so phosphorus, here we have the 3 unpaired electrons in the p suborbital, and here we have this one paired up one. So when you start to remove this guy, that's actually what the atom wants, because it doesn't really like to have these paired electrons. Okay, so that means that when the electrons are paired, the extra mutual repulsion of these two electrons in the same sublevel will mean that it requires less energy to remove the electron, hence the reduction in the ionization energy. So look at the graph below. I'm going to give this as a longer task, okay, in class. So looking at the graph of ionization energy against atomic number, I want you to answer two questions. Explain what the graph shows in as much detail as possible, okay, explaining why it's the shape it is. And also, there's two breaks, okay, well, it's actually about 3 breaks in the general pattern. And why do you see this particular break? And explain why that is. Okay. So looking at now ionization energies down the group rather than across the group, ionization energy decreases going down a group. Okay. Going down a group in the periodic table, the electron removed during the first ionization is from the highest energy level, and hence it is further from the nucleus. The effective nuclear charge also increases because the number of protons increases, but the effect of the increased nuclear charge is reduced because the inner electrons are actually shielding the outer electrons. So as you go down, obviously, the number of electron shells increases. Okay, so there we go. So the first one, there is high ionization energy because they're very close to the nucleus, whereas as you go further down, they're going to be further away. So another aspect of ionization energy is successive ionization energy. Okay, so we remove one electron and then we can also remove subsequent ones. Okay, it's basically successively reducing it. So here is our ion. We're now going to remove another electron to make an X2 plus ion. That's known as the second ionization energy. And you can get the corresponding third and fourth ionization energies depending on the atom or ion. So successive ionization energies increase because electrons are being removed from increasingly positive ions. Okay, the number of protons are still staying there, and we're actually removing electrons. Therefore, nuclear attraction is greater, and large jumps can be seen when the electron is moved from a new sublevel. So just to illustrate this point around successive ionization energies, let's look at the successive ionization energies for the atom of sodium. Okay, so to help with that, let's just draw the 3 energy levels of sodium. Okay, so you're going to have 1 electron on the third shell, going to have 8 electrons in the second shell, and the closest to the nucleus is going to have your 2 electrons. Okay, so if we try to remove the first one, okay, it's going to be reasonably easy because it's far away, and also the first layer and second layer of the electron shells is going to be kind of shielding that last electron. Okay, so there we go, we just got rid of that one there. Okay, so then we go to the second energy level, and it's going to take a lot more energy, which we witness here, to get rid of this electron, okay, because it's closer to the nucleus, okay, and it's also going to have more effective charge, okay, because it's now close to the nucleus, and now you've lost 1 electron. So it's going to take a lot more energy. And then we can continue getting rid of the 8 electrons of the second shell, okay, and then we're going to remove this guy here, okay, and that's going to take a massive amount of energy because it's even closer to the nucleus. It's no longer being shielded. Okay, so the electrons on the second level were being shielded by these 2 electrons here of the s suborbital. It's no longer being shielded, so it's going to take a larger amount of energy to remove this electron here. Okay, just leaving this 1 electron, and that is reasonably straightforward because even though it's feeling the pull, you're already with very high energy levels up here anyway for that last electron. Okay, so that's an example of how we can use effective nuclear charge and the distance of electrons and how they're shielded by corresponding energy levels as an illustration to explain energy level graphs like this as you remove electrons successively and the amount of energy required to make those removals.